Some of you are taking the...
Dr.
Yes.
Chari, the one question that had to do with the character table, the answer had 8 values in it, but it was only like a 5x6 table. How do we get the 8 values?
Do you have the question in front of you?
The exam isn't up anymore.
But did you know?
I can read.
Yes. Gulveer, can you please go ahead? Yes.
Yeah, it's the reducible representation of, for the BH3 molecule would be. Is that what you meant? The one that had like many numbers instead?
Yeah, that one.
Okay.
Did you have the same issue too, Gulveer?
Sorry, what is it?
Did you have the same issues?
Yeah, I had those extra 2 numbers as well in my exam.
Oh, okay. And you got it wrong, or what does the exam say?
Well, it just added, I think, was 3 numbers at the end. 1, 2, 3, 4, 5, 6.
I don't know why it does that, because I just gave exactly. So, is it a PhD or BH3?
It's D3H, yes.
So D3H. So that's a. Can you read this here, folks? Can you see my board? Can you see the board?
Yes, we can see it.
Okay. So that's a BH3, that's a D3H group, right? So basically, if you now go to the character table for the D3H, you have E, right? We're looking for the reducible representation, which is tau R, or sometimes they say tau RR. So the way we answer this question is first we look at the identity, and to do that, we need to know how many bonds this molecule has. As you can see in BH3, it's a trigonoplanar molecule. So you have 3 bonds. So the value of E here will be 3 in the beginning, correct? And then the next one is your C3, is that correct? Does somebody have a D3H character table with you?
Yes, it's a 2C3. It's 2C3.
2C3. So what should be the value for this 2C3? So in a C3, right, you're rotating this molecule. While doing so, you're moving all the 3 bonds. So the value for the C3 will be 0. Does that make sense to you? What's the next one, folks? 2C3 and then
3C2.
3C2, great. In a C2, what we're doing is you're rotating this molecule along one of the BH bonds. So one of the BH bonds will stay in place, the remaining 2 will move. So 2 moves 0, there's 1 stationary, so the value will be 1. And what's the next symmetry operation?
Sigma H.
Sigma H. Sigma H is reflecting this molecule in a plane that is perpendicular to the highest 4 rotational axis of symmetry, that is C3. So all 3 bonds will stay in place. They don't move. They don't get displaced. So that value will be a 3. That makes sense? What's the next one, folks?
2S3.
2S3. S3, by definition, is a C3 followed by sigma H, correct? Since C3 is 0, S3 cannot be anything but 0, because S3 involves a C3. What's the next one?
3 sigma V.
3 sigma V's. The sigma V's are planes that contain 1 BH bond at a time. So you have 3 of them because you have 3 BH bonds. So when you do a reflection with this molecule, one of the bonds will stay in place. The remaining 2 will get displaced. So the net value is 1 for this. Anything else on this table? That's all it is?
Yeah, but in the problem, it added 1 0 at the end of that. So there was 301, 301, 10. So that was the question.
Oh, I see, I'm sorry, I don't know. The correct answer should be 301, 301. I uploaded a table with the correct answers, but the Canvas must have done something crazy on this. All right, so if you get a problem like this, don't worry. If you got this part right, you will get full credit for it. Okay? Other questions? Anything else on this? Any other question?
Could you go over the problem with the Jan-Teller distortion?
Sure. Olivia, do you have the example questions on this with you? Jan-Teller distortion question.
Yeah, I think it was number 12. Do you want me to read it off for you? I have it written down.
Can you read it off for me, please? I don't have that with me right now.
So the compounds were magnesium and then 6 waters with a +2 charge.
Is it magnesium or manganese?
Manganese, that's what it was, manganese.
Manganese, okay.
And then
Okay.
the next compound was the same thing, but with a +4 charge.
Okay.
And then the next one was copper with the water and then a +2 charge.
Mhm.
And the next one was titanium with water with a +3 charge.
Titanium with +3 charge, right?
Yeah.
Okay. All right, so we want to know which of these following complexes might exhibit Jan-Teller distortion, correct?
Yes.
All right, so to answer that question, we need to look at the electronic configurations in a crystal field splitting. And please keep in mind, water is a weak field ligand, which implies that the crystal field stabilization energy is very small. So that invariably leads to what we call high spin complexes. So with water, you always get high spin complexes because the splitting is not extensive. So for the manganese 2+, then we need to write down the electronic configurations for all of these guys. In octahedral, you get T2G and EG. We all know. So manganese 2+. Anyone remembers the electronic configuration of 2+? Manganese 2+. Isn't it argon 3d5? No?
Yeah, that's right.
That's correct. So if you have 5 electrons, all occupying 5 different orbitals, do you have any degeneracy or a choice of keeping these electrons? The Jan-Teller distortion comes only if you have 2 or more configurations that might look degenerate. In this case, you don't have any because you have 1 electron in each orbital. So this is not a candidate for Jan-Teller distortion. Let's go to the next one, manganese 4+. The manganese 4+ is argon 3d3, is that correct? So when you do that, you get 1, 2, and 3. Here again, you don't have any choice. You have 3 orbitals and 3 electrons replacing. So there's no choice. The choice comes if you have 1 empty orbital, right? That electron could go there or there. That choice is not existent here. So go to the copper here. In the case of copper, it is argon 3d9. So when you do that, you get this. So you have 2 orbitals. One of them has a pair of electrons, the other one has a single electron. So now these 2 are originally degenerate orbitals. That means they have the same energy. So it's giving you a choice now to keep this pair on this or this. And the nature will not allow you to take the choice. Instead, the system will split to keep the single electron up and the double electrons or the pair of electrons down. That leads to a distortion in the symmetry. So this is a candidate for Jan-Teller distortion. Now, finally, when we go to titanium, hexaaqua titanium 3 complex, Titanium 3 plus, what's the electronic configuration, folks? How many electrons the titanium 3 plus has?
1 in the 3D.
One electron. So we have only one electron right here. Now again, I have a choice. I can keep this electron here, there, or there. Whenever you have a choice like that, the nature will not give you the choice. Instead, the system will distort in a way to stabilize that electron in a low-lying orbital. Whenever you have that splitting leads to a distortion in the geometry around the titanium 3 plus. That makes sense, folks. So the answer to that question is, among the 4 complexes, the first 2 will not show under distortion, but the last 2, the copper and the titanium, will. That's all there to it. Any questions, folks, on this? Am I clear? So you can see a picture, you can see a pattern where you don't have a distortion, and you have examples where you have a distortion, and you see the difference in the configurations. It kind of will tell us why some of these complexes show distortions where others don't. I can add one more, like for example, what if I have a 3 plus here instead of 4 plus, which adds another electron here, and that throws up everything. Now I have a pair of electrons in one orbital and 2 single electrons in the other 2 orbitals. You cannot have a digital set of orbitals when you have an equal number of electrons. So this is going to distort. So manganese 3 plus shows a distortion, while manganese 4 plus will not. Neither manganese 2 plus. Are we okay, folks?
Yes, thank you.
Thank you, Chris, for asking that question. So the one that we have to deal with. I'm sorry about the D3H question. I'll check that one more time because in my faculty view, I don't have that issue, but when we look at the student view, I don't know what is going on there. I need to talk to the IT people.
Professor, I had a question for, it was question 17.
Okay.
And the question is the irreducible representation for the H2S molecule would be
Which one is this?
H2S molecule.
Okay.
So the right answer was A1 plus B2.
Mhm.
But when I did it, I got the A1, but
Mhm.
it was plus B1 and not plus B2.
I also got that one.
Okay.
Your correct answer was A1 plus B1?
So yeah, the one I got was A1 plus B1, but the correct answer based on, the exam was A1 plus B2.
Okay, what are the orbitals that we have in the A1, A2, B1, B2 representations, folks? This is a C2E molecule, right?
Yes.
This is a C2E representation, correct?
Yeah.
So can we look at the orbitals that are available under A1?
It's the s orbital.
Can you tell me what the exact numbers?
Oh, the numbers?
Uh-huh. Yeah,
So
not the
A1
num-
is going to be 1.
No, I'm not looking at the numbers. I'm looking at the representations. Is it X, Y, X squared?
Oh,
What
sorry.
is it?
X squared, Y squared, and Z squared.
X squared, Y squared, and Z squared. That is an S orbital. Okay, how about A2?
XY.
XY. All right, okay, how about B1?
XZ.
X and Z, okay,
And the last one is YZ.
YZ. All right. So what we're trying to now look at is the kind of representation. When we say A1 plus B1, right? So we're using sp2 hybridization using X and Z orbitals. On the other hand, if you're using A1 plus B2, you're using S orbital plus py and pz orbitals rather than the px, correct?
Yes.
Okay, so either one is okay, but you have to go by your calculations. If your calculations gave you the coefficient of the B2 is 1, is that what you got?
Yes, I got 1 for B2.
1 for the B2 and
I got 1 for the B1 and 1 for A1.
and 1 for A1, right? And B2 should be 0, right?
Yes.
Okay, there might be a typo then there. So, but it should be, that's the correct one.
Okay.
From a technical perspective, either one is correct because you're dealing with one S and two different P's, either P X and PZ or PY and PZ. Either way, it's fine. Okay, good. Other questions?
There were two questions that mentioned the effective magnetic moment, and I just didn't remember that.
Okay, let's go with the questions. Do we have the other questions written down?
Yeah, 11, it was which of the following complexes is expected to display an effective magnetic moment of about 8 Bohr magnetons?
Mu effective of 8 BM, okay. And what are the choices you have there, folks?
A was K4 EU CL6. B was RU H2O6 3+ complex. C was CR NH3 6 2+. CR.
CR, sorry. CR NH3 6+. Okay,
Is that 2+?
I said I put 3+ there.
Yeah, I think it was 2.
2+, okay. CR 2+.
Right.
Oh, thank you, yes.
And then the next one was NaAlCl4.
Na,
AlCl4.
AlCl4. Okay,
And then there was also FeCN6 4- complex.
4-, okay. Okay, so there are two ways of approaching this problem. One is to find out the number of unpaired electrons on each of these complexes, right? And then calculate the effective magnetic moment. Basically, the effective magnetic moment, as you all know, is square root of n times n plus 2, where n refers to the number of unpaired electrons the system has, right? So if you were to have an 8, can you solve for the value of n?
It should be 7, right?
Yeah, around 7. And value will be approximately 7. Now we want to identify a complex that has 7 unpaired electrons. Okay. Now, if you look at this choice, sodium aluminum chloride, that is sodium tetrachloroaluminate. Right? When you look at this one, aluminum 3+ has 0 electrons. Because aluminum is in the group 3, right? Remember boron, aluminum, gallium, they're all in the group 3. On the right-hand side of the periodic table, when you remove 3 electrons, you effectively leave with nothing. So this is 0, so this cannot be a choice. Similarly, if you look at FeCN6 4-, Fe in this complex is in 2+ state, correct? In iron 2+ state, we have what we call 3d6 electronic configuration, but the Cn is a strong field ligand. So when you do the splitting, you get 1, 2, 3, 4, 5, 6 here, and again 0 unpaired electrons. Right? So let's go to the chromium 2+. Chromium, as you all know, is 3d 5, 4s1. So when you look at chromium 2 plus, we have argon 3d4. That means I have 4 unpaired electrons. So that's not the choice either. In general, when you have complexes like ruthenium, osmium, and things like that, even if you have a weak field ligand, they always give you so low spin complexes that you don't have that either. So finally, I have europium 2 plus. Europium 2 plus is a 4f7 system. So there are 7 electrons in 7 f orbitals. So the correct answer for that is going to be KPO-CO6. That makes sense, folks?
The only thing I don't understand from it is that how can you graph those 7 electrons based on the model, based on the EG and T2G? Like, how do you graph those 7?
Okay, you don't have to worry about that for 2 reasons. Number one, the Cl is a weak field ligand. When you have a ligand that is weak field, it always gives you high spin complexes. So when you have 7 unpaired electrons in the presence of a weak crystal field splitting ligand like chloride, you're going to retain all those 7 unpaired electrons, and hence the answer is going to be 7. You will have a tough time if I were to give you a strong field ligand, like a cyanide or a carbonyl or ammonia or EDTA. I didn't do that. Does that make sense?
Yes, thank you.
Great. So I'm glad that we are covering this. It's excellent. Come on. The reason I threw this is, although we are not looking at the lanthanide chemistry, at least you should know the electronic configurations. Europium, gadolinium, dysprosium, chromium, lutetium, neodymium. Now, these are all the elements in the periodic table. And that's what this chemistry is. Other questions, folks? All the questions in solid state were okay? They were reasonable? Fair? A scale of 1 to 10, how do you rate this exam? 10 being the most toughest exam you ever took in your life.
Maybe a 5.
A 5? Oh, it's not bad, right? Neither tough nor too easy, somewhere in the middle. The actual exam, of course, we'll be taking, we'll be covering some of these concepts. The Antar distortion question may not come out as exactly the way it is given in the sample, but we'd like to know whether you understand the Antar distortion.
Professor, I have a question for number 9.
Mhm.
It says, consider the 3 complexes MX3, MY3, and MZ3
Mhm.
with visible absorption wavelengths of 420, 650, and 360 nanometer respectively.
Mhm.
The crystal field stabilization energies for the ligands X, Y, and Z can be arranged as, and you have to arrange them. So the way I thought this is that, if you increase the stability, that means it's going to have a large splitting between the EG and the T2G. And so that means you need a smaller wavelength.
That's correct.
Okay. I just wanted to make this out.
Yes, because if you look at the delta E, right, that's HC over lambda. So the splitting energy is inversely related to the wavelength. So smaller the wavelength, larger is the splitting. So we say the Z produces a stronger crystal field compared to either X or Y. Between X and Y, Y produces the least amount of splitting, right? While X is intermediate. So the order of the strength of the ligands is going to be Z is going to be the strongest. That's number one, followed by X, followed by Y. That's 2 and 3. In fact, this is how scientists determine the crystal field effects of newer ligands. If you make a new complex, you do an absorption spectroscopy and then find out where is it absorbing that lambda value, and then use that lambda value and quickly calculate what the crystal field splitting is. Make sense, sir? That's good. You're thinking right.
Okay, thank you.
Other questions?
I'll ask one more.
We can
That
ask.
was question 19, and he said the compound K2 bismuth can be considered as the right one was zintal phase. I don't remember like what the zintal phase was.
If you go back to one of my lectures on the solid state chemistry, we remember we classified the solid solutions as alloys, intermetallics, interstitial solid solutions, substitutional solid solutions, right? And also as zintals. Now, zintals are generally formed when you have a strong electropositive metal, such as potassium, which is located in the leftmost corner of the periodic table, to that of a main group metal, which is extremely on the right-hand side. It's a p-block metal. These are basically called main group metals. So when you have an alkali metal, which is highly electropositive, and a bismuth, which is highly electronegative, although both are metals, but one is highly electropositive, one is highly electronegative, that combination always gives you zintal. In the class, we gave examples like NaTl, right? If you go back to our lecture notes, you would have seen I called NaTl as zintal because sodium is electropositive, thallium is electronegative, and for the same reason, potassium bismuth must be considered as a zintal because it is electropositive and electronegative combinations. That makes sense?
Yes, thank you.
Okay, thanks for asking. Remember, the job is not to go over all the topics, just to go over the exam to see what concepts are troubling us so we can review them again, make sure that we will not make that mistake in the actual exam. As you know that I have not graded that exam, so you would not have received a grade for that, did you? Other questions? Anything else that is making confusing or something is not making any sense?
I had a question for number 8. You were supposed to determine the formula of a compound.
Mhm.
So it was in a cubic structure, capital A type atoms occupy body center position, and B type atoms occupy centers of edges.
Okay. The body center is A and the centers of edges are occupied by B, right?
Yeah.
Okay. And we want to know what the empirical formula of this unit cell is, right? So we again go by the effective number of atoms per unit cell. If something is inside the cube, then it will contribute 100%. So it's A. Although you have 12 B atoms in the structure, any atom on the edge of a cube contributes only 1/4. So we have 12 B's with only 1/4 contribution. So the formula will be AB3. Is that the correct answer, folks?
Yeah, that's the right answer. I just had my fraction wrong.
Okay, all right. Yeah, so always remember inside one, if it is in the corner, it's 1/8. If it's on the face, it is 1/2. If it's on the edge, it is 1/4. So if you remember this, you'll be fine. Should there be a question asking you to find the stoichiometry of a compound, this is how you look at the unit cell and know what compound they're talking about. Thank you. Any other questions? When I looked at the statistics, I did the analysis. Most of you did reasonably good. Maybe a couple of questions you got wrong, not because you're not doing it right, it's because it's not showing up right in the canvas. So I was a little worried before, but now I understand. So, I feel much better now. So I'm confident that you all will do really well the first exam. The test run was good. Any other questions?
I had one more for it was question 2,
Okay.
where you're supposed to find the radius of a copper atom.
Mhm.
So it says the cubic close packing structure has a density of 8.93 grams per centimeter cube, and then you find the radius from that in picometers.
And they tell you it's copper, right?
Yes, copper.
And they want you to find the radius of the copper?
Mm-hmm.
Okay, great. All right, so how do we do this? Can anyone help me with this? So it's a face-centered cube, right? So we have copper atoms at the corners. And then we also have atoms at the centers of each of the faces. So the effective number of copper atoms here. What's the effective number of atoms for the face-centered cube, folks? What did we say in the lecture? It is 1, 2, 3, or 4?
Isn't it 4?
Oh, yes.
Correct. Good. Yeah, you can unmute your thing and give an answer. That's the 4 atoms. So if I know the density, right? And what's the value of this cell? Did they give you the unit cell value here? The edge of the unit cell? No? But we know that we have 4 copper atoms, and we know the atomic weight of copper, right? So once I know the atomic weight of copper, I can find the molar mass of copper. And if I know the molar mass and the density, if I know the mass and density, I can find the volume. If I know the volume of the cube, then I can take a cube root of the volume of the cube to get the value of the cell parameter, which is the edge of the cell. That's the length that we're talking about. Once I know the length, then along the face diagonal, you have the atoms touching. So that is square root 2 times A, which is 4 times the radius of the copper. Once you know the A value, you can find the R, which is the radius of the copper. That is how the strategy is. Did anybody get it right? Because I don't have the calculator in front of me, but this is the strategy that you follow.
The only thing I had trouble understanding is how did I know this was going to be a face-centered cube? It just said with the
Cubic
cubic.
close packing is synonymous
Okay.
with face-centered cubes. It's a good question. CCP, cubic close packing, is synonymous with FCC, that is face-centered cubes. So in the scientific literature, some people call this as a face-centered cubes, and some people call this as a cubic close packed structure. It's a matter of semantics. The other structure, of course, is HCP, which is hexagonally close packed structure. If that is the case, they would have told you so. They said it's face-centered cube, so we're just fine. So find the mass of the 4 copper atoms, and from there you can calculate the, the density. So you can find the volume, from volume to cell edge to the radius. Is that clear, folks?
Yes, thank you.
Excellent. Thanks for asking. Other questions? It's a lot of stuff you need to review, right? I mean, if you go from the beginning to where we are, we've covered quite a lot of ground. So you need to review each one of them. As you can see in the sample exam, you will not see a question that was not covered in the lecture. So if you followed the lectures properly and all the example problems that I gave you during the lectures, I don't see any issue. I mean, most of you have done really well, And I'm not worried about a lot of people failing at all. In fact, you're all going to do very well. But pay attention to the details, review the material one more time, read everything. Like, for example, the K2BI and NATL, right? If you had not read the lecture, you would have missed that point because the Zintels are slightly different than intermetallics. Okay. Any other questions, folks? If I don't hear anything, I don't want to waste your time because this is a prep time for the exam. We've done a sample, we have reviewed the exam, and once we have sample review and your lecture, next Tuesday, I'm going to take the exam, and following Thursday, we're going to continue our lecture, and we're going to start the topic of redox chemistry, especially from an industrial perspective, and then we're going to do a lot of stuff that you may not have even heard in Chem 2, like Frost diagrams, Latimer diagrams, and quite a lot of interesting stuff. All right, so we'll see you, and I wish you good luck with your exam on Tuesday. You'll have the exam available for you, just like the way the sample exam was available, 120 points. If you have any issues, just complete the exam anyway and send me an email saying that we had an issue with this question. Like, for example, if you see 2 additional numbers in the canvas, then please let me know by email. Okay? If not, I wish you all good luck. And we will see you next Thursday at the same time. I think we're going to have a daylight side savings, right? It's going to be interesting for some of you. All right, see you then, folks.
Bye, Chari.
Thank you very much. Thanks for coming to the class.
Thank you.